So if we're trying to find the derivative of inverse functions, we have to use all of the tools that we have so far. We're going to use implicit differentiation, and we're going to end up using the chain rule as well as some other stuff that we are going to have to remember. So let's say, for example, we have our function. Let's say we're trying to find the derivative of inverse tangent. Okay, so since we don't have anything to start off with, you might be tempted to use the definition of the derivative, but we don't have any identities really that would help us. So instead of doing that, let's instead use the definition of just a general inverse function. So I'm going to call this guy y. So if y is equal to the inverse tangent, what that means is that x is equal to the tangent of y. And so this is just the definition of the inverse function. When you say what's the inverse tangent of x, what you're saying is what's the input that gives you an output of this guy. So that's just the definition. Now notice though that this looks an awful lot like the implicit differentiation problems that we've done already. And so even though we're looking for the derivative of this function, or in other words, so we're looking for, let's make sure that we're clear, we're looking for the derivative of y with respect to x, or y prime, whichever way you want to call it. Okay, so if I write down, let me just write down this guy again, x equals to tangent y. And let's say I get the derivative of both sides. The left side, using implicit differentiation, I get the derivative of the left side and the derivative of the right side. Okay, so the derivative of the left side, the derivative of x is just 1. Now the derivative of tangent of y, again, notice that, remember, y is a function of x, right? We have it right here. And so we have to use the chain rule. So the derivative of tangent is secant squared, and then we leave the inside alone, so y stays the same, times the derivative of the inside, which we're going to symbolize by dy over dx. Or you can also write y prime if you want. Okay. And then, well, essentially what we're doing is we're trying to solve for dy over dx, right? So dy over dx is equal to 1 over secant squared of y. Now, so that's the derivative, but notice that, you've got a y in here. And that's not really what you want, because you want to go from this guy, which is a function of x, you want to have x's in here. And so you might be thinking, well, what can you do? But you might kind of remember, well, hey, you might be able to turn this guy, since you're trying to go to x's, turn this into an x. There's a couple ways you can go about it. Notice that you can write tangent of y in terms of x. So if you can turn secant into tangent somehow, you can write it in terms of x. So you go, aha. Aha. You remember you had an identity that looked like sine squared. Let me write it as y's instead so that we don't get confused. sine squared plus cosine squared is equal to 1. Okay, and from this if you divide everything by cosine squared, you get the identity that you need, which is tangent squared y plus 1 equals to secant squared y. And so notice that this guy right here, you can plug it in right here, and you might be wondering, well, how does that help me? Well, also notice that if this is tangent squared y plus 1, but what's tangent squared y? Well, that's right here. This guy, tangent squared, is just x squared. And so then in the end, what you have is that the derivative of y with respect to x is 1 over 1 plus x squared, or x squared plus 1, whichever way you want to write it. So if the function is, so what that tells you is that the derivative of inverse tangent is, is 1 over 1 plus x squared. Now, how about inverse sine? Well, you can do something similar. Let's say, for example, you have y equals to inverse sine. And if you want, press pause right now and try to drive it yourself, see what happens. But I'm gonna continue on in a similar fashion. So if I rewrite this, this is x is equal to sine of y Actually, well, you guys try that. Why don't I instead, let's do a different perspective. So you can do it that way. It's, but I kind of want to show you a different way to do it, just for fun. Okay, so I'm going to use an identity. And the identity is that sine of inverse sine. So what is that? Think about that. What is sine of inverse sine of x? Well, if you said that that's equal to x, that would be exactly correct, because these guys are just basically undoing each other. Okay, so that's good. Now how about if we, from this, get the derivative of both sides? So let's say I get the derivative of the left side and the derivative of the right side. So similar to the last one we just did. Now on the left side, you would have, you have to use the chain rule here, of course, because you have a function of another function. So the derivative of the outside, so this is the outside, and this is the inside. The derivative of sine is cosine, and then we leave the inside alone. Notice that this one doesn't have any y's whatsoever, so there's no no y's in here. Okay, and then so the derivative of the outside, leave the inside alone, times the derivative of inverse sine. But hey, we don't know the derivative of inverse sine. So I'm just going to write it, let me choose a different color. I'm just going to write it as the derivative with respect to x of inverse sine, with the understanding that, hey, this is what I'm looking for. I don't know it, but this is exactly what I'm looking for. Okay, and this is equal to the derivative of x, which is simply 1. Okay, now since this is what I'm looking for, the derivative of inverse sine, well, you can move this guy over by dividing both sides. So then what you would get is the derivative of inverse sine is equal to 1 over cosine of inverse sine of x. Okay. And then, so here you need to find cosine of inverse sine. You have a couple of options. You can use the, so you have a couple options. You can use the identity. Sine squared plus cosine squared is equal to 1, like we did in the first example, the first derivation. But since we already did an example doing that, so in that, using that, you would turn cosine into sines, and then you can use the first identity that we used right here. But let's use right triangle trigonometry. Okay, so you have to remember your trig if you're going to do this, but let's call this inverse sine of x, let's call this theta. Okay, so if this is theta, and remember that inverse sine is only defined between negative pi over 2 and pi over 2. So if you don't remember that, you have to go back and review your trig, but remember we have to chop it so that it's 1 to 1. But anyways, it's between negative pi over 2 to pi over 2. Okay, now that is important because cosine is always positive between negative pi over 2 and pi over 2. Okay, so that's why that's important. Now, let me draw a right triangle. So if I draw a right triangle, and let's say this is theta, then what this is saying is that theta is the angle. Theta is the angle. Okay, are you guys paying attention? Theta is the angle such that sine of that angle theta is equal to x. So if sine of theta is equal to x, that means, and remember sine is opposite over hypotenuse, then this side would have to equal to x, and this side would have to equal to 1. Because then you get sine of theta equals to x over 1. Okay. That means that this side down here, by the Pythagorean theorem, is equal to the square root of 1 minus x squared. By the Pythagorean theorem. So then, cosine of theta, cosine of this angle right here, which is adjacent over hypotenuse, is going to equal to the square root of 1 minus x squared over 1. So then what that tells me is that the derivative of inverse sine is equal to 1 over the square root of 1 minus x squared. Ooh. That's it. So now we have, for the general case, for the derivative of inverse functions, it equals to 1 over f prime, so the derivative evaluated at the inverse function. Or another way of thinking about this guy is, think of this guy as y. So, where does that one come from? Well, similarly to how we did the inverse sine, you have f of f inverse is equal to x. You get the derivative of the left side and the right side. And it's, pretty much the same thing. On the left side you have that this is equal to f prime of f inverse of x times the derivative of the inside, which is f inverse of x, is equal to 1. And then you solve for this guy right here, and you end up with this formula down here. And so really that's all there is to it. And actually, once you have this formula, you might want to try this with the two derivations we just did. You can use this formula to derive the other two as well. So lots of options. That's why math is great.